In the previous session, I draw a diagram. There was a typo in it, as I discussed it with I. Now, it was for these four fundamental subspaces, if you remember. What is the name of this one?
Range of A.
Range of A. This one, we said that A is taking it here. This is?
Null space.
Null space. This is?
Null space of
A transpose. Or orthogonal complement of RA. Orthogonal complement of NA. And then this is orthogonal complement of RA, which is null space of A transpose. Now, then, if A belongs to R3 by 4, then all the things that we have written would be correct. In other words, here we will have 3 4 by 1. Three by 1. 1 4 by 1 and 1 3 by 1. And this is from Rn. This is from Rm. And this is m by n. And let's do a numerical example. Assume A is 1, 2, 3, 1, 1, 1, 1, 1, 1. Okay, can you give me the numbers for A? A belongs to R. What is M? What is N? What is R?
3 by 3.
3 by 3. What was the rank?
2 probably, because
Yeah,
they are the
because
same.
one of the columns has been repeated. So what about RA? RA is a span of, easily we can see it, right? RA,
Why is the rank 2 again?
these are the same, aren't they? How many linearly independent columns do we have? It was too easy to see it's linearly independent. So, what about NA? It's a span of, for example, let's pick up this one, and if it is multiplied by 0 minus 1, 1, it will take out into 0, right? Now, we want to calculate what is the NA orthogonal complement, and what is RA orthogonal complement. In order to find them, we have to come with a set of vector which can help us to span the space which they do not belong to RA, right? Because they're complement of each other, and it will be it does not belong to NA. So, and it is equivalent to this. Now, in order to find the NA orthogonal, how many vectors will we have there? Look, how many columns did we have? In general, 3, right? One of them is in NA, and in here we need to have 2 because they need to be, when we add these two, when we do the direct sum, we have to get R, isn't it? So we understand that in here I need to have 2 vectors, and in here I need to have 1 vector. And what is the characteristics of this? So in here we know that there should be a span of 2 vectors. But what are the characteristics of these 2 vectors? We know that if I have a dot product of this vector and this vector, I will get
0.
0. This vector and this vector, I will get.
Also.
Why? Because they are orthogonal. They are perpendicular to each other. Okay, can you tell me that one of the vectors?
Probably 0, 0, 0 or.
0, 0 is the trivial solution. One can be like 1, 0, 0, because if I do the dot product, I will get 0. Another one can be 0, 1, minus 1, for instance. No, 1, 1. Because a 0 by 0 is 0, 1 by minus 1, minus 1, 1 by 1, 1. If I add them, I will get 0. Right? You can write here, I don't know, 2, 0, 0. You can have a combination of these ones and put them. It doesn't matter. Because when you use the S-span means that any type of combination can be each of these vectors. And for this one, how many vectors I will have? Because this had 2, definitely this has 1. And we know that it has to be a vector, which if I multiply with all the vectors that I have in there, I have to get 0. Right? Because this one is orthogonal to this one. So this dot product with this vector should become 0. This dot product with this vector should become 0. And of course 0, 0, 0 is not an option. I mean, with a little bit of thinking, we can come with any combination, any set, any vector, because we are writing S-span means that whatever you want to. For instance, I can tell you that 1, minus 2, 1 is one option. Minus 1, 2, minus 1 is another option. Because if you do it, it will be 1, minus 2, plus 1, which is 0. It will be 1, minus 4, 3, which is 0. Yes, Ike?
Yeah, so if you want to use the other way and say A transpose, then find the range of
Yeah.
A transpose. How do you arrive at the complement of the null space of A?
Well, if you do the transpose of that one, what is the vectors that we get? Is this, isn't it? The matrix that we get is this 1, 1, 1, 2, 1, 1, 3, 1, 1. Right? So we have to find sets of vector which is actually spanning this. Let's see if this is spanning this one or not. In other words, pick up any vector in here. Can we write it as the linear addition of these two? Yes. For example, let's say the third one, it will be 3, let's call it V1 plus V2. How can I find easily this spans by looking at it? Well, I can see that all these ones are 1, so this is 1. What is left is alpha 0, 0, isn't it? And the easiest one is to normalize 1. Are you good? So my apology, you were right, that should be, I wrote it previously 4 by 3, it has to be 3 by 4. So if you go back to your slide, your notes, you have to correct it. I don't erase this example because I want to ask a question about this example, and before that I want to write a definition. We remember we had two terms, onto and one-to-one, right? And we said that an onto means that by using this linear transformation A, we are covering all the elements that we had in the codomain, right? But now we have two more definitions. Actually, it's a theorem. And it says that let A to be from Rn to Rm. Then A is onto if and only if rank A is equal to M. But we need to put one more condition in here. I'll write it in a few seconds. A is one-to-one if and only if rank A is equal to N. Here we have this condition, A transpose is not singular. And here we have A transpose A is not singular. So, question. No question. Finish writing the answer. Now the question is that this example that we solved, is A one-to-one or is it onto? it is onto and one-to-one. Any other opinion?
Well, there was, I think, in one of them that the null space should be 0, and
No,
here it's not.
And why do you go to null space? I mean, you have the definition here. Look, what is the rank? What is the rank?
Yeah,
2.
Yeah.
What is M? 3. What is N? 3. It says that in order to be one-to-one or onto, we need to have like either M equal to rank or N equal to rank. And here, M and N are not equal to rank, so it is not onto, it is not one-to-one, as you said, non-exclusive. So, now we use this in order to have a little bit more definitions. Given A, the linear transformation, B from V vector space to W vector space is called invertible, or we call it bijective. Invertible, or we call it bijective, if and only if A is one-to-one and onto. In other words, A is invertible if and only if dimension of V is equal to dimension of W. So for A going from Rn to Rn, it is invertible or non-singular if and only if rank of A is equal to n. Then we have two definitions which makes us to be ready for the next chapter. And this last term was something that you might remember from undergraduate algebra. Now, given A again from vector space V to vector space W, then what? A is said to be right invertible if there exists a right inverse transformation such as I changed the color because this one stops acting. A minus R from W to V vector spaces such that what do I have to write here?
A multiplied by A minus R.
There you go. A is said to be left invertible if there exists a left inverse transformation and minus L again from W to V such that what do I have to write here?
I minus L multiplied by A.
A minus L multiplied by A is equal to I. Now, one thing that you have to note, okay, finish writing, but we need to go back and add a few more things to these writings. A very minor thing. But where does this I belong to? And where does this I belong to? In other words, do they belong to the W vector space or do they belong to the V vector space? When it is in the right inverse, it belongs to W. When it is on the left, it belongs to V. In other words, this one, we have the right inverse if we are only onto. And we have only left inverse if we are only one-to-one. Remember, if it is only onto or only one-to-one, and we have this right or left inverse, they are not unique. They are not unique. You can find sets of vectors or matrices which are satisfying this condition. Which leads us to the theorem that I will write in a few seconds. So we start to see that there are some inverses which are not unique, and they are called right and left inverse, because till now we had either no inverse or we had one inverse, which was unique, right?
There's a thing in MATLAB if you cannot find an
Yes,
inverse
I
line.
know.
Yes, is that connected with this
Yes,
thing?
this is the next chapter that we want to study. So
Okay.
this is joining us to the next chapter, which is called pseudo-inverse. In MATLAB, it's called P-inv. And the theorem is this. Let A to be from vector space V to vector space V if there exists a unique A minus R, then A is invertible. If there exists a unique A minus L, then A is invertible. Okay? So this means that we can actually come up with a set of matrices which are not necessarily a square, but they can take us to the identity matrix. This is very useful if we want to find some solution for sets of equations where our equation is overdetermined, for instance. Do you know what is the term overdetermined? Overdetermined means the number of equations is more than the number of unknowns that we have in our hand. So in such cases, we can come and use these terms. Now, up to now in the let's say undergraduate level algebra, we always had this inverse existing if it was an S-square matrix. And then we were checking if the determinant is non-zero, because if the determinant was zero, we were calling it a singular matrix, so the inverse does not exist. So now we started to define that, okay, we can come up with the sets of results, which is not unique, but lead us to be to get to this identity matrix. Now, this means that we start a new chapter which is talking about Moore-Penrose pseudo-inverse. We will see how we can calculate. It's not easy to calculate it. In general, in order to calculate this type of matrices, especially if the sizes are big, we need to use lots of numerical analysis, but some of them have a straightforward formula which we will discuss about it. So the chapter is Introduction to Moore-Penrose how to spell pseudo? Pseudo-inverse. And as Donna said, in MATLAB, we had a comment which does that. It's called P-in, which you can find the inverse, the pseudo-inverse of a matrix which is not a square, a matrix which is singular, and then we will start to talk about the pseudo-inverse from right, the pseudo-inverse from left, and we see that under which conditions actually the pseudo-inverse is an equivalent to the actual inverse. But before we started, I need to tell you the homework, right? And we have 11 questions. Let's pick up 5 numbers between 1 to 11. Ike?
1.
1. Hassan?
7.
7. Anna?
3.
3. Ike?
5.
5. So let me choose one also. 10. Because difficult ones are at the end. So 1, 3, 5, 7, and 10. Can you give me your pen?
Oops.
I will put the questions as usual into the module, and since I put it, you have 2 weeks to solve it. So what was the problem? The problem was that we actually are facing in the reality, especially in computer science, we are facing with images. We are facing with vectors or matrices that we need to calculate their inverse. But we find out that they are not a square or they are singular. So what happens is that we cannot calculate the inverse by using our traditional methods, but here algebra helps us by having the pseudo-inverse. Suppose that you have we have a system of equations, but systems of linear equations. To solve. But you have, instead with B, you stick with B. We have more equations than unknowns. The system is, we describe the system in this form. A is equal to AX, I mean traditionally. So what are the knowns, what are the unknowns here?
Y and A are given, and
Yeah, they are known,
yeah.
and X is the unknown, and the aim is that to calculate the values for X, right? Where A belongs to R n by n, X belongs to what?
M by 1.
Rn,
X, okay.
and Y is Rm, right? Y is Rm. So if we have So if the matrix A were square and the determinant of A was not 0, we could say, what could we say? We could say this, y is equal to ax, so I multiply both sides by a minus inverse of a, and this was I, so I will get a inverse y is equal to x. If A was a matrix and it was not singular, right? Whereas it's not the case, because here we have a general A, which is, as you can see, not a square. Which is not our case, as A is not a square. Hence, conventional A inverse cannot be calculated. It cannot be calculated. However, a pseudo-inverse can be formed, and we represent the pseudo-inverse by A plus. This is a notation that we define for pseudo-inverse. So let's